I'm going to talk about an important part of the TensorFlow-Lite micro library design, its interpreter. TensorFlow Micro is based on an interpreted approach. So what's an interpreter? Interpretation means executing a program by following a data structure stored in memory, as opposed to a purely compiled approach, where execution is determined by instructions ahead of time. In our case, this is a difference between storing a model as data and looping through the operations at runtime, calling appropriate functions based on the op type, versus examining the model at compile time and omitting code that makes direct call to the functions. But aren't interpreters slow? The most common place you have encountered interpreters and compilers in the past is on desktop computers. Python is an interpreted language and C++ is compiled, for example. Broadly speaking, desktop interpreted languages are easier to use, but run more slowly. Is this true for embedded ML too? Running a procedural language like Python through an interpreter is inherently challenging because each line of code probably only takes a few assembly instructions to execute. These are very simple instructions. There are many simple instructions together for each line of code. But parsing that line, in Python to actually breaking it down for the interpreter to make sense of it may take thousands of instructions. So this gives a big performance advantage to compile languages like C++, which do the parsing ahead of time, right, at compile time. So machine learning is different though. In machine learning, each layer like convolutional, softmax is likely to take tens of thousands, even millions of cycles to execute. This means any parsing overhead is comparatively small. As a result, there isn't a noticeable speed difference between the approaches, of real models, in our experiments. As a practical example, an experiment was run to count the number of instructions that were taken up with interpreting the model versus calculating the operations. That's interpreting means that we're parsing it and then actually executing the actual operations, that the model is using. So for a large model, it's vanishingly small proportion of time that's taken for parsing. And even for a very small model, it's only a few % of cycles. And there's some very important advantage to using an interpreter. It's possible to change the model without recompiling the code. Though, a lack of file system on most embedded systems make this a little hard in practice. The same operator code can be used across multiple different models in the same system. And the same portable model serialization format can be used across a lot of different systems. So how does interpreting a model actually work? Well, the model contains a list of operators and arguments. For example, conv2d, fully connected, softmax. The interpreter loops through this at runtime and calls the appropriate operator implementation or kernels. You can think of the interpreter as pseudocode that loops through a list of ops for each one that decides what function to call based on the op type.